This video is on higher order derivatives. And if you already know how to take derivatives, the good news is that, this isn't really any more difficult than doing that. It's just making sure you understand, terminology and what you're trying to do. So let's start with an example here that says to consider this polynomial. All right, this would be true for any function, really. If I had y equals, say, x to the fifth minus 3x to the fourth plus 2x cubed minus x squared plus 4x plus 1. Then say I asked you to find the first derivative. Right? So then we're looking for y prime. If I asked you to find y prime, you take the derivative like you normally would. For a polynomial like this, use the power rule pretty easily. You would have the derivative of x to the fifth would become 5x to the fourth, subtracting 1 there from the exponent, minus, remember the 4 comes down, so it'll be minus 4 times 3 is 12, x to the third, plus 2 x to the third, the derivative of that, 3 times 2 gives you 6, x to the second, minus here, bring the 2 down, will be minus 2x to the first power, it's minus 2x, and then plus derivative of 4x is just 4, derivative of 1 goes to 0. So there's y prime. Alright, so that's the first derivative. Now, suppose I asked you to take the derivative of this. Well, we call that the second derivative, which we label as y double prime. Alright, so the two little dashes means the second derivative. So you're taking the derivative of the derivative. It's not any more challenging than what we just did, right? It's really the same thing, it's just different values. So 5x to the fourth, the derivative of that, 4 times 5 is 20, and we have x to the third, minus 3 times 12 gives me minus 36, x to the second, plus here 2 comes down, 2 times 6 is 12x, and then derivative of negative 2x is just negative 2, derivative of 4 goes to 0. So that's the second derivative. And you could continue on like this. I could say take the derivative of this. We'd call that y triple prime. It would be the third derivative. And if I did that, 3 times 20 would give you 60x to the second, bringing that 3 down, reducing the power by 1, minus 2 times 36 is 72, x to the first, plus derivative of 12x would just be plus 12. Derivative of negative 2 goes to 0. Let's keep going just to show you what would happen. Fourth derivative, we don't usually put, after 3, we don't put the little lines there. We put this little like parenthesis with the number of the derivative in it. So this means the fourth derivative of y with respect to x. 60x squared, the derivative of 2 times 60 would give me 120. This would be x to the first power, minus derivative of 72x, which is minus 72. Derivative of 12 goes to 0. The fifth derivative of y, right? Derivative of 120x is just 120. Derivative of negative 72 goes to 0. The sixth derivative, right? Derivative of 120, well, it's a constant, so that's 0. What's the seventh derivative? Well, the seventh derivative would be derivative of 0 is 0. And eventually, they would be 0 all the way down, right? It could keep doing this, and they'd always be 0. Now, that's not always going to be the case. It's always going to be the case for a polynomial. Eventually, you can get to a derivative where you always will have 0. But it's not the case for all functions. So let me give you another one just to show you the difference. If I said to consider y equals x to the 3/4 power. If I wanted to take the first derivative of this, y prime, the 3/4 would come down in front, right, using our power rule, and then we have x to the 3/4 minus 1 would be negative 1/4. And then if I was trying to find the second derivative, so the derivative of this, now if you want to rewrite this, that's okay, but then you have to undo the rewriting to find the next derivatives, because you don't want to rewrite this with the x's in the denominator, because then you couldn't use the power rule. So y double prime, the second derivative, right, so we have double prime there, you're going to follow your power rule, right? So you're going to bring the negative 1/4 down times the 3/4. So it's really going to be negative 3/16 x to the negative 1/4 minus 1 makes that negative 5/4. Because remember, really you're just taking away 4/4. So negative 1 minus 4 is negative 5, and then it's over 4. And you could keep going like this, right? So that's the second derivative, the third derivative, multiply this back down. Negative 5/4 times negative 3/6. Negative times negative makes it a positive. 5 times 3 is 15. The 16 times 4 would be 64. So 15/64 x to the, subtract 1 from this exponent. Negative 5/4 minus 1 is negative 9/4. And you could continue on like this, on and on and on, right? I'll do one more just to make sure you see it. If I was saying the fourth derivative, I'm looking at here, bringing this down, negative 9 times 15 will give me a negative 135 over 4 times 64, which give me over 256. X to the, subtract 1, negative 9/4 minus 1, which is minus 4/4, would make this negative 13/4. And you could keep going, right? I could take derivatives forever on this, and I'm never going to have this come out to 0. So even though the previous one did for a polynomial, for other functions that's not always true, and you have to watch out for that. The other thing to point out on something like this, notice the signs are alternating, right? Because you started with a positive and became a negative, and negative times 5 made it negative, and the next one would be a negative times a negative made it a positive, and so on. So just something to point out. Watch your signs when you're doing this, because they do change. So, just generally speaking, I'm going to do some examples with it. Right? The second derivative, and that's when we're going to talk about, or the highest one we're usually going to talk about, I should say. The second derivative of y equals f of x is written as, you just saw it a minute ago, y double prime, which equals, you can write it as f double prime of x, right? So two little lines there means second derivative. Or in the Leibniz notation, you have d with this little 2 up here of y, means the second derivative of y with respect to x. Right? So this means take the second derivative of y with respect to x. You know, they're interchangeable. You don't really have to use one notation or the other. Just make sure you know them both if you see them. So, for example, suppose I said for y equals 3 over x, find second derivative of y with respect to x. Well, the first thing you want to do is notice that you should rewrite this, because x is in the denominator. Don't let us use our power rule. We needed x to a power. So we got to move that x up. So the rewrite, remember, it's still the same function. It's y equals 3 stays 3. This will be x to the negative 1 power. Remember, the power in x is 1, so moving it up makes it negative 1. And then let's take the derivative. So we need the first derivative before you can get to the second derivative. So I wrote it as y prime. You know, maybe I'll write it the way they asked us. So I'll write it in Leibniz notation. So dy over dx, that would be equal to, well, taking the derivative, negative 1 times 3 would be negative 3x to the negative 2. And remember, I was asked to find the second derivative, so I want the derivative of that. So the second derivative of y with respect to x, that's the derivative of this. Negative 2 times negative 3 would be positive 6. X to the, subtract 1 from the exponent, negative 2 minus 1 is negative 3. So you got 6x to the negative 3. And simplifying this, we want only positive exponents in our answer, so I'll write it as 6 over x to the third. And that would be the second derivative. So in order to get to the second derivative, you have to take the first derivative, right? It just has to be that way. Let's take a look at just a few more. So for this example here, if I said for y equals the square root of x cubed minus 9x, all right, so the square root of x cubed, and then minus 9x is not underneath the square root. Find y double prime. Well, first thing I want to look at here is rewriting, because I have this radical in here. I need this to be just x to a power. So first thing, we'll rewrite the original function. We got y equals. Now how do you rewrite the square root of x to the third? The base is x. The power on it is 3 over whatever the root is. Square root means over 2. Right? So square root has an index of 2, so it's 3 over 2 minus 9x. And now we're ready to find the other derivatives. So y prime, the first derivative, I'll bring the 3 halves down in front here using the power rule. We have 3 halves x to the power is 1 half, right? 3 halves minus 1 gives you 1 half, minus the derivative of 9x, which is minus 9. And then we want to take the second derivative, right? So we got the first derivative. They asked us to find the second derivative. Don't forget to do that part. You've got 3 halves x to 1 half. You bring the 1 half down. 1 half times 3 halves. Remember how you multiply fractions? Straight through the numerator, straight through the denominator. So 3 times 1 is 3. Over 2 times 2 is 4. So you got 3/4 x to the 1 half minus 1 is negative 1 half is the power. And then negative 9, the derivative of that just goes to 0. So you're left with 3/4 x and negative 1 half. And now we just want to simplify this. To simplify this, the negative exponent tells you to move it to the denominator. So you have 3 over 4 x to the 1 half. And then if I write it that way, this would be 3 over 4. X to the 1 half power means square root. So 3 over 4 square root of x. I'm okay with you leaving it like that. You may have learned how to rationalize in the past. Maybe I'll just show you how to do it here quickly, right? I'd multiply by the square root of x for each of these so you don't have a radical in the denominator. So you'd have 3 square root of x over 4 times the square root of x times square root of x is just x, because it's really the square root of x squared. That's why we did it. So 3 square root of x over 4x might be how you see it. I would be okay if you left it this way without rationalizing. Either way is okay. As far as turning in work for this course. If you're doing this through, software like my math lab, you might be forced to rationalize or not, depending on what the directions say. Let's take a look at another one. So if I said for y equals x squared plus 8x raised to the 9th power, find y double prime, find the second derivative. So first thing we want to do is find the first derivative. To find the first derivative, we have a function raised to a power. Remember, this is a function inside of a function, so we're using our chain rule. We call it extended power rule. It's really a chain rule. Chain rule says you bring, take the derivative of the outside first. Derivative of the outside says bring the 9 out in front. Keep the inside the same, x squared plus 8x, and then subtract 1 from that exponent. So that's the derivative of the outside, and then you multiply it by the derivative of the inside. The derivative of the inside, derivative of x squared is 2x, plus the derivative of 8x is just plus 8. That was the first derivative. Now we need the second derivative. To get the second derivative, you really want to look at this in terms of, all right, this is a function times a function now. I can't bring the 2x plus 8 into here. I can't get rid of the parentheses here. I need this to be a function times a function because you can't simplify that much further. In doing that, you want to look at, okay, what's the first function, what's the second function, and then we're going to use a product rule. So now we have a product rule problem. All right, so we're going to use product rule. To use product rule, remember, I'll call this whole thing the first, and I'll call this whole thing the second, just to make it easier to work with. So when we find the derivative, the second derivative now, we're using product rule. Remember how product rule works, right? If I have a function times a function, you take the derivative of the first and times the second, plus the derivative of the second times the first. So let's do that. So the derivative of the first, and derivative of the first here, the 9's a constant in front, the 8 will come down, so 8 times 9 gives me 72, times, now within this first part, we're using what? We're using the chain rule, so 8 times 9 is 72, the inside stays the same, don't change that. Subtract 1 from the exponent makes that 7, and then times the derivative of the inside, so derivative of x squared plus 8x is 2x plus 8. Now that's all just, let's make sure we see it. This was f, this is g. This is all f prime. So it's all the derivative of the first. Alright, and then we're going to multiply that times the second, which is g. So this would be just times 2x plus 8. So this 2x plus 8 came from when we did chain rule on this, when we took the derivative. This 2x plus 8 is just times the second, right? So the derivative of the first times the second, that's our chain rule, plus the derivative of the second. Well, the derivative of the second, 2x plus 8, the derivative of that is just 2, right? So that's my g prime for using the notation we did when we did chain rule, or product rule. So derivative of the second is just 2 times, you leave the first the same, so times 9 times x squared plus 8x to the 8th power. And this whole piece is just times the first. So the derivative of the first, derivative of that, times, you leave the second alone, plus the derivative of the second times whatever the first is. Okay, second derivative, if I asked you not to simplify, you've got it, it's done. But if I did want you to simplify, you should have an understanding how to simplify this. We end up with y double prime is equal to. Now here, I'm just going to simplify this as 72 times x squared plus 8x raised to the 7th, and then 2x plus 8 times 2x plus 8 is 2x plus 8 squared. Plus here, 2 times 9 would give me 18, and then the x squared plus 8x is raised to the 8th. Do not distribute 2 through this, right? This is all multiplication, so it's just 2 times 9. You can't multiply into this because the 8th power on the outside of it. And you actually could simplify this a little further if you wanted to factor out a GCF. You know, this looks like a nice form, but if you wanted to factor out a GCF, you could. 72 and 18 have a GCF of 18, so you can factor out an 18. Remember, this is a term and this is a term, so I'm looking for greatest common factor between them. So I can factor out 18. This is x plus x. This has x squared plus 8x to the 7th. This has x squared plus 8x to the 8th. When you have the same factor, remember you want to take the lowest power of the factor you see out when you factor, because that's the largest one they have in common between the terms. I can't factor out any of the 2x plus 8 quantities squared because there are none over here. So when I factor that out, what am I left with? Well, 72 factoring out the 18 gives me 4. This whole x squared plus 8x to the 7th factored out, and then you have 2x plus 8 quantity squared. Plus here we factor out the 18, and we're just left with the x squared plus 8x to the 8th. We took out 7, so we just have x squared plus 8x to the first power. You know, I'll put the parentheses here so you see it, but you really don't need them because it's a plus. If it was a minus, you would need the parentheses. And now let's simplify the inside of this. We have y double prime equals, this is 18 times x squared plus 8x to the 7th times, this is 4 times, if you FOIL this, you know, expand this 2x plus 8 quantity squared, remember it's 2x plus 8 times 2x plus 8, you'd have 4x squared plus, you get a 16x and another 16x, so plus 32x, and then plus 8 times 8, so it'll be plus 64, and then plus x squared plus 8x. There's nothing to distribute, you can just drop those parentheses. And we'll simplify this just a bit more. We have 18 times x squared plus 8x to the 7th times, you're distributing the 4 through this. So 4 times 4x squared is 16x squared. 4 times 32 is plus a 128x. Don't lose the x. And then 4 times 64 is plus 256 plus x squared plus 8x. And then we can combine like terms. So y double prime in the end is 18 times x squared plus 8x, that quantity to the 7th power. And then times 16x squared plus x squared is 17x squared. 128x plus 8x would be a plus 136x, and then plus 256. And you could leave it like that. In all honesty, I'm doing this so you understand where the answer came from if you see something that's expanded more than what we normally have. If I said, you know, just do not simplify. Find the second derivative and do not simplify. I really want you to leave it like this. This is what I'm looking for. If you have to simplify it, then you have to go through all of this. If I ask you to simplify though, or if I don't ask you to not simplify, then it means you should simplify. The other thing is when you're checking answers while you're doing homework, a lot of times they'll simplify it. And if you just saw this as the answer, it doesn't look like what you have up here. So I want to make sure you understand how to get from one to the other and to ensure they're equivalent. So that was taking the second derivative. Some of the examples are more straightforward than others. The next thing we'll look at is applications of the second derivative.